everyone. Welcome to the crash course for multi-age systems, the extremely high speed crash course. It's only 2 sessions. Right. So what are we going to do today? I'm going to first give you an introduction to, myself and this course. We're going to go through the planning and exam analysis. So looking what's most important to learn for the exam. And the topics that we're going to talk about today are prologue and some theory about agents and environments. So no marble just yet. First, about myself. Hello, my name is Salem. I'm 21 years old and third year Bachelor AI. So I took this course just last year. I'm not a TA for multi-agent systems, but I am going to be TA for project multi-agent systems. And yeah, for everyone, the request to turn on your webcam, and yes, I see camera faces popping up. So yeah, I'm really used to giving classes in real life, and it's very helpful for me to see everyone. I have a second screen where I can see the chats as well as everyone else. So it would be very helpful if everyone turned on the camera. This is the second group. No, this is the QR code for the WhatsApp group. If you haven't joined already, please do now. Here you can ask questions to each other and to me. And in general, this is just some extra support for the exam outside the sessions. So someone's asking me if it's okay to not turn on webcam. Well, if you really don't want to, I can't force you to, but yeah, the more people turn on the webcams, the more helpful it's going to be. About the structure, so we're going to have a lot of topics, and for every topic, ideally there would be a bit of theories, an example, and a practice question. Not all topics are equally difficult or big, so some might miss the practice question, or we'll take some together for practice questions. We're going to base it on past exams a lot, because since we don't have a lot of time, we will be focusing on passing the exam. It's highly recommended to just ask questions, and I don't mind being interrupted, so you can just turn on your microphone at any time. And yeah, we can ask more questions in the WhatsApp group later. So the planning. Today we're mostly going to talk about prologue and the environments and agents. The theory about environments and agents is not a whole lot, so we're not going to spend a lot of time on that. We'll mostly be doing prologue. And maybe if we have time, a small introduction to Marble. But we need prologue to do Marble anyway, so that's why we're doing prologue today. Next session, we're going to go in depth about Marble, and also practice a lot with prologue and do a lot of practice in general, because prologue is really something you cannot learn unless you practice it a lot. The exam. So based on past exams, that is about the structure of the exam. You will first have a pretty significant part about the basics of prologue. Then a smaller part for the more difficult prologue things. There will be a small part about theory, and about half will be Marble. So, well, a lot of points are for Marble, which is also why we're going to spend a lot of time in it in the second session. You really need prologue to understand it. And we're going to do basically everything except Marble today, hopefully. All right. Any questions about the planning and maybe any requests? Don't necessarily imagine there are. But yeah, so if there's anything at all, just interrupt me anytime. This is also the first year someone from Athena Studies is doing a crash course for multi-agent systems. So feedback is very much appreciated. Right, let's jump right into prologue. because Prolog is very different from Python and whatever other languages you've done before. And the reason for this is it's a logic-based language. So if you've ever heard about the generations of programming languages, not very important, but this is the fifth generation, which means that you're really expecting a lot from the computer, as in you're not giving it a step-by-step guide on how to solve whatever you want it to solve. Instead, you just tell it, what is the situation and what do I want solved? And then you expect it to solve it for you. Is Prolog actually useful for doing this? Not really, because it is 50 years old. So it's not actually that great, but it's very interesting to learn. And yeah, it's very different from other programming languages. So I will not be able to draw a lot of parallels with Python today. It's really just entirely new. So what are the components of Prolog? There's two main components. The first is the knowledge base. This is the part where you tell Prolog what kind of environment we're working in. So it consists of facts and rules and basically everything Prolog needs to know to solve questions. And you have queries. Queries are the questions you ask Prolog. In a terminal, you use it with question mark dash, although you're not going to be using terminals type stuff in the exam. The queries is the part where you ask Prolog to solve things for you. Right. Let's just start with the basic syntax. I'm going to go through this really rapidly because these are the basics that most people really already know. So we have atoms and variables. Those are the basic components of Prolog. An atom is usually a value. So anything you put in quotation marks or anything starting with a lowercase letter, usually it's the smallest units of meaning. And again, we usually use it for values, although special characters are technically also atoms, but we will not really use them in that way. Variables are variables are empty places where you can put values in later, just like what you would expect from Python variables. They start with uppercase letters or an underscore, and this is not convention. This is actually a rule of Prolog that they would start with an uppercase or underscore. So make sure you do not forget that. Underscore can also be a variable. It's a special variable because it's called the anonymous variable. You can assign values to it, but you cannot retrieve values from it. And you can also use it to basically put multiple values in. And the reason why that is use it when you don't really care about the contents of a position of an argument or something. So that's why when I read it, I read the underscore as doesn't matter, because that's how you end up using it most of the time. Some more syntax. You have the colon dash. This defines a rule. I'll explain what a rule is in a bit. Comma is a conjunction. A semicolon is a disjunction. Stuff you probably already know. The forward dash and then a number defines the amount of arguments for a predicate. This is not something you put in the code itself, but more when you describe a code on paper. So you just tell how many arguments it takes. Facts. All right, so then you have the knowledge base, which consists of facts and rules. Facts are just bits of information that you can use, but you don't do much with. So the names start with the lowercase letters. Then you have parentheses in which the arguments live are inside. Some simple examples. You have a car. You have an instance of a car called a Volvo. You can have another instance of a car called Audi, whatever. And then child, we can have the child predicate has, for example, two arguments. Then you have rules. Rules are more like functions. So things that actually actively do stuff. They work in logic theory. You would represent them as an implication. So if A is true, then B must also be true. A in this case is the head. This contains the name and the input variables, and B is the body, which contains whatever the rule does. An example is child name parent A and parent B. These are the this is the head. Then this is the indicator that it's a rule, and this is the body of the rule. So whatever you fill in here, because these are empty variables, whatever you fill in here is a child if and only if these rules are true for whatever you put in. But we'll get to more examples later. First important actual working of Prolog, instantiation. This is something that if you didn't catch it in the beginning of the course, it will give you trouble for the rest of the course. So instantiation is the process of giving an empty variable a value. Instantiating a variable, it gives it a value. In Prolog, it calls onto the value and cannot be changed until the search ends. So until it discards the value for whatever reason. In search, Prolog automatically instantiates, but you can also, in rules, manually instantiate with the equal sign and the is. So the equal sign is used for general strings, facts, numbers, etc. While is can only be used for numbers and it only instantiates one way, and it evaluates the right side. But I'll talk about is in more detail later. So our first couple of examples of actual code. Instantiation. Fill in a variable with a value. That's basically in the most basic case what instantiation is. So x equals 5. What it does is it instantiates x and gives it the value of 5. So whenever you read x, now you read 5. It's basically how you would normally assign a variable. Oh, one more thing. In Prolog, every line ends with a dot. I forgot it here, as you can see. And in the second line, we use is, x is 5 plus 7, evaluates the right side. Evaluating in Prolog means you do the math, so 5 plus 7 equals 12, and then instantiate x for 12. But like I said, we'll talk about this later. So, a first couple of practice questions. What will the answer be for the first query? This is for you guys to answer.
Do we need to type it in the chat, or
you can type it, or you can just say it?
Okay, false, of course.
All right. Yeah, exactly. It's false because in the first part it instantiates x for 5, and in the second part it instantiates x for 7. However, x already contains a value. It's 5. 5 is not the same as 7, and so the second part fails, and because it's a conjunction, both of them have to be true or succeed, which in this case it's not. So yeah, it fails. How about the second one? I already see some answers in the chat. However, it will not output true because I'm assigning a value, so it would tell me what it assigned instead of just saying true. So what would it assign in, what would the output be in the second query? Anyone else?
5 or 7?
Not exactly. So actually, do I have?
Yeah, x is 5 or x is 7.
Right, but it wouldn't say x is 7 because what it does is it instantiates x for 5. That succeeded. Then it tries to instantiate x for 7, but that fails because it's already instantiated for 5. But because this is a disjunction, if the right side fails, it doesn't fail the entire query. So it just outputs x equals 5. Just to note, these are edge cases. So you won't often find queries like this. But I figured since we're just doing the basics, we might as well go as far as we can. Now for the last one. Yeah.
X equals 7.
Right, and can you explain why?
Because the left side fails because it assigns it to 5, and then it says is x equal to 7, and then so it's only on the right side.
Yeah, exactly. So, like you said, the left side fails, and because the left side fails, Prolog deletes the instantiation for 5. However, just because the left side fails doesn't mean the entire query failed. So the right, because it's a disjunction, so the right side can still continue. And this is a bit unintuitive to think about. So if anyone doesn't understand still, feel free to ask. But it ends up throwing away 5, then continuing because it's a disjunction. So there's still a chance that the right side can succeed. And because x is now empty again, it can instantiate for 7, and that's its final answer. Right. That was weird, but that was instantiation. Again, if I'm going too fast, let me know. Next, we're going to talk about search. So, a couple workings of Prolog search is, first of all, it's exhaustive. I actually have annotations. Oops, where's okay, that was weird. So first of all, it's exhaustive. So it will search the entire file, and in some cases, it depends on what you ask. But for example, sometimes you'll ask it, give me all occurrences of something, and it will search the entire file. It's that first search. That's just the inner workings of Prolog, but considering the scope of this crash course, we will not actually talk about this a lot at all. It instantiates variables whenever it needs to. We'll see that in a bit. If at any point it fails, it will go back to its previous decision. What I mean with decision is the previous time it instantiated a variable, and it will check, do I have any other options? And if it does, it will try other options. We'll also see that in a bit. Names can be reused. This is the case for both facts and rules. In fact, you can sometimes have a rule and a fact by the same name. And in that case, it will just evaluate them in the order that they're written down in the knowledge base. The closed world assumption. This is probably mentioned once during the course. It means that if we have a knowledge base and we assume that knowledge is all knowledge there is. So if we ask something and it's not in our knowledge base, we assume it doesn't exist. This is the opposite of the open world assumption, which you probably had in knowledge and data, where if there is something missing if you ask something and it's not in your knowledge base, you say, well, we don't know, but someone else might, so we cannot assume it's false. But here we say, if we don't know it, then nobody knows it is false. Lastly, negation by failure. We'll take a look at that a bit later as well. It means that instead of proving that something is false, we just check, can we prove it's true? And if we cannot prove it's true, then it's false, which is a weaker version of negation. Like I said, we'll take a look at it a bit later. So, another example, we have a knowledge base on the left, And on the right, we have Prolog's interpretation of what we just wrote down. So you see 3 facts, 2 cars and a scooter, and we see 1 rule. This rule can be read as X is a vehicle if and only if X is a car or X is a scooter. Of course, these words that are starting with lowercase letters are atoms, and these variables that are starting with capital letters are variables, which means they are empty unless we instantiate them. So, some basic queries. Can someone give me the answer for the first 3? They're pretty similar, so answer if any you like.
True, false, true.
Right, and can you explain, I guess, the third one?
Okay, so the third one, X is Vespa. So then scooter Vespa or scooter X is true in the knowledge base.
Yes,
It's
let
a
me just
disjunction.
draw it out. So we're looking for a vehicle. Vehicle. Ah, hey, look, vehicle. It takes 1 input. Well, we have 1 input. So we instantiate X for Vespa. Now we look, is there a car by the name of Vespa? No, there is not. Is there a scooter by the name of Vespa? Yes, we found one right here. It's a disjunction, so only 1 needs to be true. So we just found that true. Therefore, this also returns true. Basic, right? Now we're asking, give me all cars. Because we're inputting, instead of inputting an atom, we are inputting a variable, which means I'm asking for cars specifically, I don't know, just give me all of them. So what will the output be? X equals Volvo and X equals Ferrari. Indeed, and I just realized I made a mistake in the next slide. I'll show you the answers. I accidentally put Vespa in there, so this one should not be there. Any questions about basic search? All right. We shall continue. A more complicated example. Just to really get the hang of search. Anyone have the answer for the first one? So we're querying, is Ferrari a car?
True.
Yep, because while there is no car explicitly says Ferrari, we do have a rule for car, and as you can see, it's the same name, but that's okay. Prolog just checks the first one, and then it goes from top to bottom, checking all of them. Ferrari. So X is a car if and only if X is also a fast car. Well, Ferrari is a fast car. We found right here. So this returns true. X equals vehicle. What will it return? X equals Volvo and X equals Vespa. So why not X equals Ferrari?
X equals Ferrari also.
Yes, because let's just go through what it does. X is a vehicle if and only if X is a car or X is a scooter. And we just established that Ferrari is also a car. So what's going to end up happening is it's going to have an empty variable. It's going to go through this, and for every car, it will instantiate X with the argument. And here, it will do the same thing as the vehicle rule and input X. So we'll ask for every X, for every fast car that you find, also instantiate X with that. So
yeah,
it's just
I pressed enter before it looked good, so I answered a bit too quick. So,
yeah, no problem.
Yeah.
It happens. So you're gonna find that most examples that I have in here are very unintuitive because I'm trying to look for those edge cases where you might make mistakes. And this is actually where I was supposed to put X equals Vespa. I put it in the wrong slide. But yeah, that should be included. Like X equals Vespa. But yeah, continuing on. Let's take a look at batch tracking. So I think it's best if I just put the answer on screen right away and walk through what's going on, because I'm asking specifically for the trace. Not entirely sure if that's exactly the correct syntax for trace anymore. This was a while ago, but that doesn't matter right now. So let's take a look at an example for backtracking. I'm asking it, give me all fast cars, because I'm putting in a variable. All right, well, there's only one occurrence of the name fast car in the launch base, is this rule. And we're going to input an empty variable in it. What should I... An X is a fast car if and only if X is a car and X has a turbo. So first we're going to look at a way to instantiate X for car. We're going to find Volvo first because it's on top. So we're going to instantiate X with Volvo. However, once we get to this clause, we're going to check if X also has a turbo. X equals Volvo. X does not have a turbo because there's only one turbo, that's Ferrari. What you're going to see is as soon as we ask, does Volvo have a turbo, we're going to get false. And this is a conjunction, so the entire thing immediately fails. However, for lock will not give up because it has an option, backtracking. So it accounted a failure. However, it still has other options to instantiate X with. So it's going to take a look. It can also instantiate X with Ferrari. So X is now Ferrari. It will ask, does Ferrari have a turbo? Yes, it does. We found one. That's true. So we have an answer, namely X equals Ferrari. Because we asking for all occurrences, it will backtrack again and check if it has any other options because it's trying to find every single occurrence. But of course, there are no other options, so it doesn't do anything else. Final answer, we found only one occurrence. Questions? If so, interrupt me or write in chat. Next topic, unification. Unification is like instantiation, but next level. Because the equal sign can do one more thing. It can also do unification. And what it means is if you have two terms on either side of the equal sign, for A and B, it would try basically to make both of them equal to each other. So it will try to make sure that A is the exact same as B. And there are three ways to do it. First of all, the first way to do it is if both terms are already the same, then we're already done. So we don't have to do anything. That was simple. If one of them is a variable, or both are variables, then we can instantiate one variable with the other. In other words, we just do instantiation with, like we just saw. So if a equals 5, it will unify them by instantiating a with 5. It also works the other way around. So it doesn't matter where the variable is, it will instantiate them both ways. If they're both variables, then it will instantiate the variables with each other. Doesn't matter. It can do all of them. Third one is the most complicated. If they are compound terms, meaning if they have more than one atom in it, as I say, most often you will find it as a way of facts, right? So if something like this. So this is the most complicated way of unification. If both sides have like complicated terms, it can instantiate it, but there are some more rules because it's more complicated. First condition is that they have the same outermost functor, in other words, the same name. These are the D's in outside the parentheses in this case. So they have to be of the same type. Second condition is that the terms match. Realistically, this means that they have the same amount of terms, both of them, which in this case they do. Third rule is that when instantiating variables, we should not encounter any problems. If the instantiation fails, then the unification also fails. Let's look at some examples. First query is child Jessica Dave equals child X Dave. Can someone give me the output for this? So Prolog will be trying to unify these.
X equals Jessica.
Yes, indeed, that was a very quick answer. So it doesn't matter where the variable is, they have the same outermost functor, they have the same amount of terms, and it can instantiate X for Jessica, and there are no further problems, and then they are the exact same. How about the second one? What's the output here? How about someone who hasn't replied anything yet, just to mix it up a bit? Anyone else? It's kind of annoying that I can never see who's typing in the chat, because that way there you go. See, that's what I meant. X equals Jessica. Right, so what I'm guessing you're thinking is that it will instantiate X for Jessica and then try to instantiate for Dave, but that doesn't work. However, the problem is that when instantiating X for Dave, it's already instantiated, which means it runs into an error. And one of the rules of unification was that you should not encounter any problems with instantiating. So in this case, it will just output false. Does everyone understand why? If not, I'm just going to assume I'm going to see some kind of question. Third one. X equals Jessica. That was really quick. I didn't have to ask for an answer. But yeah, it's correct. Because we're using different variables, we can instantiate them both with different terms and of different atoms, and we don't run into the issue of trying to instantiate a variable twice. And just for clarity, I put the variables on this side this time, just to show that unification can work both ways. So these are the final answers. I'm guessing you guys have a pretty good grasp of this by now. It looks of it anyway. It's going very smoothly. Right. Next topic, operators. Prolog has a lot of operators. And every operator has very specific rules, and it's just a lot to remember. So that's why we're going to go through it. First operator that we're going to talk about is the equal sign. It tries to unify both sides. It returns false if it fails to unify. It does not evaluate math. It doesn't do math. I don't blame it for that. And it can instantiate variables. Then there is the backward slash equal sign, which returns true if they cannot be unified. And this is again the notion of negation by failure. It does not try to find two items that don't match. Instead, it checks, can I match it? And if it's false, it returns true. And if it's true, it returns false. We'll check out a example of that in a minute. The double equal sign asks, checks if they are equal, but does not do any unification. And it also does not do any instantiation. So it's direct comparison. Are they the same? If not, then false.
So that has the same kind of meaning as a double equal sign in Python. It's like equals to.
Yeah, it's
Like a conditional.
very similar.
Okay.
But the single equal sign, for example, is quite different.
Okay. That's assigning values, and the double equals is like a conditional statement kind of thing.
Yeah.
Okay.
The backward slash double equal sign does the opposite of the equal sign, right? That much is clear. Then we have the backward slash plus and the not. These are the exact same, just as different ways of typing it. And they return false if the subgoal is true, and vice versa. And this is again the concept of negation by failure, and we're finally going to go through a example of that. Right, so the not operator, as well as the not equal, does not let you achieve the opposite goal. We'll take a look at the example. So we have a knowledge base consisting of just two facts. Sam is A, Ben is B. So our query is, I guess I'm missing a question mark, that doesn't matter. Our query is not AX, BX. In other words, the idea of this query is find me an X, or a person in this case, who is B but is not A. However, while we do have such a person, it returns false. And why? Well, what happens is it tries to achieve this subgoal, right? So it tries to instantiate X for an atom A, and it finds such an atom, namely Sam. So X is instantiated for Sam, which means that this subgoal, you can imagine parentheses around this, this subgoal succeeded because we did find such a person. However, there is a not in front of it, which means that if it succeeded, say false. And if we failed, say true. We succeeded, therefore false. And this is a conjunction, which means both have to be true. But one of them is false, so it fails the entire query. And when this happens unintentionally, it's called floundering. So when you run into problems because of negation by failure. Does anyone know a way to fix this query so that it does return Ben?
You should put the B first.
Yeah,
And not
exactly.
negation first. Don't start with negation. Or negation with not thing.
So we should first ask for b of x and then check if it's not a. And what it does is we first look for a b, so instantiate x for Ben, and then check is Ben not Sam, which is true. So then it returns x equals Ben. Floundering is probably another term that you heard once during the lectures that I never understood. At least that was my experience from multi-age systems. Arithmetic. So these are more operators, but these are meant for math and numbers. So the previous operators are meant for everything, and they do not do math. These are meant for math and not necessarily instantiating. So the is operator is the most confusing. It's very specific in its operation. So it evaluates the right side and checks if they are the exact same. I guess this wording is not perfect. It should say instantiates the left with the right. So x is 10 plus 2. What is does is it evaluates the right side and then puts it into the left side. It instantiates it with the left side. So this is 12. We have a variable here, so x equals 12. I probably shouldn't even use the equal sign because it just gets confusing with the actual equal sign. Because what it doesn't do is it does not evaluate the left side, so you should not put math on the left side, and it does not instantiate the right side, so you should not put variables on the right side. It's a really specific operator. All right. So then we have this operator. I call it the math equal because that's, I think, describes what it does pretty well. It does not instantiate anything at all. It just evaluates both sides and checks if they're equal. And I have a very specific example here to show the difference between the two. So if we say 1 is the sine of pi divided by 2, sine of pi divided by 2 returns 1, but as a float, because that's how the function works. 1 cannot be instantiated to 1.0 because they're different data types. So this fails. If we put an x here, it will instantiate x to 1.0. That's fine. The math equal evaluates both. So we'll say 1 equals 1.0. But it doesn't. It checks if they're equal instead of checking if they are if it can instantiate it. So in this case, it would succeed. Confusing, am I right? Here are some more math operators. These work in the exact same way as the math equal sign. So the not equal and the bigger than, smaller than. They all evaluate, but do not instantiate.
Can you use a variable on the left side of is?
Yes, but not on the left side of, not on either side of the math equal, and also not on the right side of is. Only here.
Okay, but so, and the variable on the left side of is, would that be the same as using an equal sign as is?
The difference between is and the equal sign is also that is evaluates the right side while the equal sign is not.
Okay.
We'll get into some examples right about now. So
one question. If you
Yes.
go one slide back, So with the equal sign dot equal sign, if like on both sides it would be a variable, but the same variable, like x and x, would it then be true? Or would it still, because it's a variable and it isn't instantiated yet, still, I think, give an error in that case because it's not used correctly? Or would it
I
just give
have
false?
not checked that exact. I haven't checked that exact example,
Okay,
but I
I don't
luckily
think it matters, to be honest, but I was just curious.
no, but it's alright because I happen to have a terminal on my second monitor open just in case.
Okay.
Yeah, like you said, it will say error not instantiated.
Yeah. Okay, what I thought. Okay, great. Thanks.
No problem. So can anyone tell me the answer for the first one? So 12 equals 5 plus 7.
False,
Yes, and why?
because the right side is not substantial. What's it called? Initiated and
Evaluated.
evaluated.
Yes, exactly. So this one is false because yeah, exactly what you said. So how about the second one?
True.
Yeah, and why?
Because 5 plus 7 is equal to 12. And now you use like the is operator, and that's the is. So that's why.
But would the third one then work?
I personally don't think so. Maybe, I don't know. I don't think so.
The third one I think is false because
Yeah, me too.
Yeah, and now it's because the like I said, the is, but yeah, again, it's they're very specific rules, right? So the is evaluates only the right side. So here the right side is evaluated and becomes 12. Here it is not. It's not evaluated. So the second one is true and the third one is false. Second one works and the third one doesn't. Right. Fourth one, would that work? Maybe some of the less active people could try again. False. Do you mind explaining why, if you want? Because it does not unify, it evaluates both sides correct, so it's true. I see two opposite answers here. So if we take a look at what the equal sign does, the double equal sign, that's not on here, it's here. So it checks if they're equal without unification. So it doesn't evaluate either side. It just checks if they are exact same. And yeah, so the double equal sign does not evaluate and it does not unify. It's really lazy actually. So it doesn't evaluate, which is what we need here because it's math. So it turns out false because 5 plus 7 is not the same as 12. One way to look at it is imagine if in Python, if you were trying to compare two numbers versus two strings. See, this one will be true, and this one will be false. And it's the same principle that's going on here. It's because it's not the exact same. It's like we're comparing strings. And for Prolog to not be evaluating it as strings, it needs to evaluate it. So unless it evaluates, it's almost as if it's comparing strings. So if you put strings around these, suddenly it kind of makes sense. But you shouldn't put strings around these because the is actually evaluates the right side, but it doesn't evaluate the left side. Confusing, isn't it? Joshua and Rishabh, would you like to try the last one? Either of you or both? True. And indeed, it checks if they are equal, so it's true. Yeah, it checks if they are equal, and crucially, it evaluates both sides. Evaluates, yeah, exactly. You guys are 100% correct. It evaluates the both sides, so it ends up checking if 12 equals 12, which is true. So, and just to repeat it, these are all the places where you could put a variable and it would not break the entire thing. You cannot put any variables here. Nor can you put any variables here. All right. On to the next topic. Oh, and here are some the answers just for completeness. We're gonna continue on to the practice exam because we actually have already learned enough to do the first 3 questions of the practice exam you guys have for this year. We're just gonna go quickly through it and we're gonna have a break afterwards. Are they 3 questions? Might also be 4 questions, doesn't matter. First is gonna be a practice in operators again. So yeah, it's just asking you a query and ask you what Prolog's answer would be for these queries. Would anyone like to answer the first one? X equals 4 plus 3. And notice has a single equal sign. X equals 4 plus 3. Exactly. It just says, all right, that must be it then. It's like putting a string into a variable. It does not evaluate them. But it also doesn't see a reason to say false. Second one. What might the second one be? This is practice in unification, of course.
Capital A equals small b, capital B equals small a.
Exactly. So let's go through the 3 rules of complex unification again. They have the same outermost functor. They have the same amount of terms. And when unifying, it tries to unify A to B, to small b, which works. And it tries to unify B to small a, which works because it hasn't used B before, it's still empty. Both succeed. It's not, both sides are now the same, and it didn't run into any trouble. All right, third one.
False.
False, and why?
Because it says that if one of the sub goals, right, is not true, then it succeeds or is true. But there's only one sub goal, and if n5 is instantiated, so that's true. So I don't see the reason why it would be false. But that's my reasoning. I could be totally wrong.
No, it's okay. So what you said is correct. This succeeds. N is 5, which is just a simple instantiation. The sub-goal succeeded, therefore it flips the true into a false, and the output will be false. I will also show the answers in a bit.
But would n equals 5 output true without the negation?
It wouldn't output true, it would just output n equals 5, but that's the same as succeeding, right? So it didn't fail.
Okay. So that backslash plus just always just makes it false, basically.
No, because if it failed, for example, if you said 4 equals 5,
Okay.
then it would say true, because
Okay.
then the subgoal failed. All right, clear so far? All right, going at this in a nice pace. So next question is another case of unification. I'm starting to forget the words. Anyway, false. And do you have the explanation why? A equals B, B equals C. All right, you're getting there, almost there. Yeah. So let's see what's going on here, because there's a special case we haven't talked about yet. It's what happens when you're instantiating variables with other variables, because the behavior is a bit different. So it instantiates A with B. So indeed A equals B. It then instantiates A with C. Now we thought, or we learned, that we cannot instantiate iter twice. However, or instantiate a variable twice. However, in this case, we are instantiating with other variables that are also empty. So there is still, we don't know what is in B and C, and we also don't know what is in A. We only know that these two arguments must be the same, right? So Prolog will think, well, if A equals to B and A equals to C, then B is C. Now I don't know, A equal, like, if this is the complete output, I don't think it would necessarily be wrong. But in the answer of this practice exam, it only mentions B equals C. I'm guessing they thought it was sufficient information.
Isn't it because A it's 2 times like the same, so that would indicate that B and C should also be the same. So that's the reason why B equals C is like the final answer.
Yeah, that could be, but now it's more like human reasoning, and I'm not sure exactly how
Yeah.
Prolog deals with it. But yeah, I imagine it's something like that. X plus 2 is 5. This is a nice edge case, but I think we have learned enough to know this one. Any takers?
False.
False. And why?
Like you explained earlier, only with the is the right side is evaluated, and X isn't instantiated and has a plus, so that wouldn't work anyways. So it's false.
Yeah, if you remove the plus 2, it would work, but it's there, and it does not evaluate the left side, which it should do in order to make this work. But therefore, it fails. Here are the answers again. If anyone has any questions, now is a good time to ask them. I'm going to continue, but if anyone was typing a question, just finish typing the question. I'll just go back to it. That's no problem. All right. Next question. Next task, I guess. For the following question, assume the following prolog base. So this is our knowledge base, and it's asking us again to give prolog's answers to these questions. Any takers for the first one? Maybe some people I haven't heard yet, like Noor, Daniela, Zoe. Daniel, no, Daniel, no, I don't know how to pronounce it. Doesn't matter. First one would be false. Well, let's see. So we have the first question, is Bill a man? Why, yes, he is. We just found it here. Is Bill a husband? Yes, he is. Not. So if he is, then false. So we have true and false, and this is a conjunction. So the answer is false. Next one, man X, not husband X. X equals Dilbert. Right, you guys work on events. That's nice. Well, let's see. So it first tries to find any X, so it will find Dilbert because he's a man, right? So it instantiates X with Dilbert. Then it goes to the second one. Is Dilbert a husband? He is not. So that is true. So we found X is Dilbert. Then we backtrack, see if there's any other options. We find Bill is also a man, so we instantiate X with Bill, but that fails here. So that one is not an answer, and there are no other options. So X is Dilbert. Speed it up a bit. How about the third one? Any takers? True. All right, let's look at it again. Dilbert is a husband. He's not, therefore true. Dilbert is a man. True. Yeah, this one is pretty simple. This one is interesting because we learned about a very special word that describes what's going on here. What's the output for this one?
False or fail.
Right, and why? What's going on here?
It's gonna fail because the not husband X is at the beginning.
Yeah, and
Which
what was it
means
called
that-
again?
Floundering.
Yeah, exactly. So it will try to find any X for husband. It can find one. It's Bill. It instantiates X with Bill, which means that this subgoal succeeds, which means that the entire thing fails. And again, the answers. Questions?
So the floundering isn't an error, it's false.
Yeah, exactly.
Okay.
It will not crash the
On the exam, should you indicate if something is an error or false? Do you think of course you cannot say that directly since you don't grade the exams. Do you think that if you say something is false but the answer is error, do you think you get like the answer is wrong?
I don't think in these types of questions they will give you any queries that have an error in them.
Okay.
We will see a question in a bit that does have an error. Oops, I spelled it. Oh well.
You mean that? Oh, I probably can guess what kind of question it is, but
yeah, no. So
okay.
an error does look different. An error is more like using
Okay.
the wrong syntax, like forgetting a parentheses.
Okay.
Question in the chat. So what happens if you turn the last elements around in the last question? Actually, it turns into exactly this, which does indeed solve floundering. So just like in the example we saw before, turning them around solves floundering in this case because it's a simple case. And it's because of the order in which you instantiate the variables, right? This one is a knowledge-based question. So any taker, so we have the following program. They call the program. They're not consistent with their own wording of what they're putting there. It's just a knowledge base. Give the outcome of follow search tree for each of the following queries. Choose between success, failure, and infinite. So in this case, they're also not asking you to give you the output, like what is A, but they're just telling you succeeded, failed, or looped forever. So any takers for the first one? It looks a bit intimidating, but if once you actually just dive into it, it's not that bad. Right. So got one answer in the chat, and I think if everyone just takes their time, they'll get to the same answer. In the interest of time, I'm also just going to go through it. So the most difficult about this is the anonymous variable, but I have a trick for that. We're going to look for a match for this query. So we're going to look for a D, because that's the outermost thing. And we can go through the entire thing and only find it at the end, because that's what these are. So the rules. The query is a D if and only if we can find an A with the content of our first argument. So can we find an A with this content? Well, let's see. A is T. No, that's not the same. A is X. That's not the same. A of B, and the B contains doesn't matter. Yes, we do actually have a B that contains doesn't matter. So we succeeded this part. Now we're going to look for a B that contains our second argument. Well, it's a Y, and there is a B with a Y in there right here. So that part also succeeds. And then not A equals B. Well, let's see. We have two arguments, and they're clearly not the same. So this also succeeds. All three of them succeed. So success. We completely succeeded in whatever we were trying to do. How about the second one? I'll clear it out a bit. There you go. Succeeds as well because of AT and BY. Let's see. So X and Y are empty, which means that we should find all occurrences. However, we should not try to find all occurrences because they're not asking us for the actual output. They're just asking us for success, failure, and infinite. So if we just find one answer, that's enough. Let's just try and go through it. Try to find any A, D, try to find any B. Why? Are they the same? No. And even if these ones were swapped, which would cause them both to be the same, we could just backtrack and find A is X. Right? It doesn't. And even if A is X didn't exist, we can always try B, doesn't matter. Like, we have a lot of options here. So we will always find a bunch of answers. So this one also succeeds. The third one is the most interesting. The fourth one is not very interesting, so I think we're just gonna skip that one. So let's do the last one. Failure because not T equals T. That makes sense because both arguments are the same. Someone asks infinite. Well, let's find out, shall we? So we have two arguments that are the same, and like Orlando says, that will fail this rule because that was one of the conditions. However, we still have a second rule that we could try. Let's put the arguments into the second rule, see what happens. Can we find a C that contains a T? We can. Okay, if so, then call rule D again with the same arguments. Calling a rule with the exact same arguments. That sounds like a bad idea. Well, okay, we're gonna search the entire thing again. We're gonna find this rule first again. This last term still applies because we're using the same arguments. So we're gonna go to the second rule. The first one still succeeds, and the third one calls itself with the exact same arguments again. We're just gonna go on forever. And indeed, you in most modern prolog systems, because computers don't like infinite loops, it's probably gonna end up calling an error because it's like it's stupid. But in theory, this will just go on forever and not give an error. So you should just say infinite. And here are the answers. Like I said, I skipped the last one because it's not very interesting. It's basically the same as the one before it, except that the C here will not succeed, so it will just not succeed either of them and fail. But it's, like I said, not very interesting. All right, last one before we take a break. I could use a break. Consider the following predicate and query. Give the output of the query and explain why this is the case. So the predicate is a rule called add 5.5 with 2 input arguments. It then uses an is to do some math and instantiate. The query says do add 5.5 with x and 3 as inputs. X is of course empty. What will the output be? It would be nice if multiple people tried to answer this one. So let's try to have at least 3 people answer in the chat. All right, I'm seeing some interesting things in the chat. Okay, so interestingly enough, it is actually not fail, it gives an error. So what happens is It's a bit of a sneaky question because the x becomes before the y, but then they use the y first and then the x. Is kind of stupid. So what happens is free is just like Rishab solved correctly, x plus 5 divided by 2. However, what does the is do? It instantiates whatever is on the left. Y is already instantiated, but that's not necessarily a problem. And it evaluates the right side. However, evaluating does not instantiate anything. And we still have an empty variable here that is not instantiated, which is illegal in Prolog. So it'll give an error. Arguments are not sufficiently instantiated. Because x must be instantiated when the predicate is queried, specifically because evaluation cannot deal with empty variables. Very fun question. Right, next up is lists. We're going to take a break first. We're going to take a break until 14:30. I'm also going to take a short break for myself, and if you have questions, please send them in the chat. See you guys in a bit. All right, I am back. Let me check the chat. Question about the thing, if you swap the variables. Yeah. Yeah, pretty much what Biren said. And I'm guessing there's a lot of questions. All right, is everyone ready to continue? I don't know if everyone's back yet. It's a bit hard to tell. Right, well, guess I'll just continue then. Where were we? Lists, right. So this will be just about the hardest part of Prolog, because we're going to do lists in order to do recursion, and recursion is the like a single hardest thing about Prolog. We're also gonna, like, when we're gonna practice Prolog again next session, we will mostly be focusing on lists, because I'm gonna try to explain. As they say list, I mean recursion, because I'm gonna try to explain recursion, but I already noticed in my previous session with another group that missing a bit of material to really go through it. But yeah, we'll get to that. First of all, lists. Lists are, of course, collections of elements. It's similar to Python in syntax, in that we're using square brackets and separating by commas. As far as I know, you can use any data type to put in it, but I'm not entirely sure about that. Not that it matters, because in this course you will only be dealing with numbers in as far as lists go. So yeah, lists can be put in a variable, as you would expect. The only difference in Prolog is that we can also separate them. We don't have indexes. That would be too convenient. We only have one way to separate lists into smaller bits, and that's by separating them into a head and a tail. This is the syntax to do that. So you have the head, that weird stripe thing that you don't usually see in programming, and then the tail. The head contains the elements and the tail contains the rest, but specifically in a list format. You can also do it with multiple heads, so you can add as many heads as you want, which makes them, you give them different names. And then it will, well, I'm guessing the slide speaks for itself, right? Necessarily, if you have only one element in the tail, it will still put that one element in the list. And if you have nothing left in the tail, it will just give you an empty list. While if you don't have enough elements for the heads, it will just not run, because you're not meeting the requirements. I think I'm saying this correctly. Yeah. So recursion. Recursion, as you guys probably know, is when a function, or in our case a rule, calls itself. And well, in other programming languages, they always say try to avoid recursion, and here it's It's all we got because we don't have any for loops. So if you want to loop through a list in Prolog, it's going to be recursion. We don't have for loops here. So the way you structure a recursive loop, if you want to loop through a list, that is, you have two rules of the same name. One represents the base case, and the other represents the recursive step. I'm trying to think if we in AI ever learned about recursion in any other courses. I might be expecting prior knowledge that is not there. But anyway, so the base case is tells the program when it should stop doing recursion, and the recursive step is simply well, simply that's the main body of the recursion. So that does all the work and also contains a recursive call to make recursion possible. So let us in detail dive into this example here. This is already a pretty, at the same time, it's pretty basic, but recursion is always difficult, so it's a pretty good example. So we have a sum. If we want to write down how to use this rule, we would type something like sum list and sum. So this rule calculates the sum of the list. You give it two arguments. One is the list itself, and the other one you usually leave empty. And when you leave it empty, the Prolog will instantiate it with it will instantiate it with the sum that it eventually calculates. You can also fill in both, and then it would just say true and false if you have the correct sum or not. But you cannot give it a sum and then expect it to make a list. That doesn't work. Doesn't work the other way around. All right. So let's look at the base case. The base case, because the base case is on top, it will always first consider the base case before going to the recursive step. And what it does is it checks if you have an empty list and the second place is a 0, then you apply to this rule, so the base case applies. And if it doesn't, if you do not have an empty list, then keep doing recursive calls. And it is very common to check for an empty list because usually we just take one element at a time until the list is empty. So let's fill in some. Right. So the recursive step itself separates the list into a head and tail. The sum, like I said, is usually still empty. So what we do is we do a recursive call. We expect a result from it. So we expect this variable, which we give as an empty variable, to return, to instantiate with a number. So r equals 5 or whatever. And then we can calculate the next step of the sum by doing the head plus the result, which both should be instantiated. So we can instantiate the sum, which is our final answer. Now this is a bit unclear, probably.
Is there a name for this type of recursion? Like when you have
We'll get to that because
Okay.
there are different types of recursion.
So I got a question, if
Yeah.
that's okay. So one of the things is, if I get it correctly, does it? So first it checks if the list is empty. Well, in most cases, if you're beginning it won't be. So head and tails in the sum, and then because like in the rule it goes to the sum directly, like sum t results. does it then first give back? So does the recursive step happen immediately, and doesn't like the next part, the sum is h plus result, does it also happen, or doesn't that happen? If you know what I mean.
No, the second part does indeed
Yeah.
not happen until we have reached the empty list.
Okay, exactly. Okay, that's just one.
And one more detail I forgot to mention is when you call the recursive step, you only give it the tail, you don't give it the head, because you're trying to
Yeah.
make the list smaller.
Yeah, I know. Okay, great. Just nice to know.
Let's
Thanks.
do a number example, because otherwise it's still really unclear. And also I find recursion hard. Recursion is difficult, and it's also difficult to explain. But yeah, let's just do a simple. We do 1 and 2 as our list, and we want to know the sum. So we just give it an empty variable. What's going to happen first? It's going to check the base case. The list is not empty, so it's not the base case. And the s, if it were the base case, the s would be instantiated with 0, but that's for later.
Sorry, can you just explain kind of the order of line priority? Because you said it goes to the base case first.
Yeah, because it's the top. So
Just because it's the top, yeah.
Yeah, so we query this.
Okay.
It's gonna look for matches of the sum. So it goes from top to bottom to check for matches, just like with the knowledge base.
Every iteration, right? So every iteration, it goes back to the top.
Yeah.
So checks if, okay, yeah.
Always from top to bottom. That's the order in which Prolog works. So it wasn't the base case. So we're gonna check the next line. And for example, if this line wasn't there, it was just a base case, it would just return false because it didn't find anything. So it's really just normal search, except we're taking a lot of advantage of how Prolog works to get some kind of functionality out of it. So like if you feel like this went off the rails a lot, makes sense. So, but realize this is just a knowledge base. This is just a fact, and this is just a rule. They're just very clever and complicated facts and rules. So, continuing with our example, it's not the base case, so we're going to the second one. Second one says if you have some kind of list and some kind of sum. Now we have a list, we have an empty variable that we can put into the sum. So this becomes 1. This becomes the list containing only 2. And this is just empty. So it's just a question mark. First we're going to do is we're going to iterate. We first encounter this recursive call. So as soon as we encounter it, we're going to run sum again, just with different numbers. Sum is the list of 2, because that's the tail we put in. And still s, because maybe it makes more sense to put r there, maybe just a question mark, because it's all empty variables, right? We call sum again with the tail and result. Result stored with a capital R is just an empty variable. We haven't instantiated R or result, so it's just an empty variable, right? So we're going to run again. And we're going to start over at the top and search again. Is it the base case? No, because we still don't have an empty list. So we're going to do the recursive call again. All right. Head is 2. Tail is empty list. Sum, we still don't know. We still haven't gotten anywhere. Well, the first thing we encounter is the sum again. This is how recursion feels for a computer. So we're going to call sum again. This time with the empty list, because we're just giving it the tail, and still nothing as the result. Now we finally arrive at the base case, and the base case works as intended. It stops the recursion as soon as we've reached a point at which we want to stop it. So empty list. So it checks out on the on the base case, so it does not search this second line. Right. What happens now? Well, the base case says your second argument is 0. I have an empty variable for second argument. So it's now going to instantiate the second argument with 0. All right, now we can go back to this call. This call was still in this step because it was busy calling this one. But it just finished that. The result is now 0 because that's what the base case gave us. All right, let's check this expression. The sum, which we don't know, is h. The h is, what was it again? The h is 2. Plus result, which is 0. We have established that here. So sum is 2. So let me just write down what we've done so far. So we have 3 calls so far. The first call called second called the third ended up in the base case, give 0 back. Second one, there calculated its sum using the result plus its head, gave back 2. Now we can go back. It would actually be really nice if it was animated or something like that.
Does that not happen in the third call though?
The third call?
Like, doesn't the sum equal 2 in the third call? Like so you've
No,
got
because
3 lines.
the third call gets called with the empty list.
Okay.
And therefore activates the base case and
Okay.
therefore returns 0. The second call was called with a list containing only the 2, which becomes its head. It receives 0 from the third call, and together with its head becomes 2, right? So that's its result. Then we go back to the first call, finally get back at where we started. The third call has as head 1. It called this sum with 2. It got back result 2. So its sum, which it doesn't know, is 1 plus 2 plus 3. Our final answer, when we call this one, so let me just write it down again. Our final answer, when we call the sum of the list 1, 2 and s, it will say s equals 3. And that was quite the journey. And I have to say, the explanation went better than last group, so can you imagine? I'll have to think of something for that. I'm gonna also clear the drawing so I can move on. All right. Yeah.
So if I get it correctly, if there, for one reason or the other, in the second part of the rule, so not of the body, so the second part of the body of the rule, so the sum is h plus result. Let's say there's an error, something that's not correct for some reason or another. Would it get to the error only after the recursion is done and the base case is reached, and then it gets to like the final part, or does it get there immediately?
Well, I'm guessing we assume the compiler does not catch it.
Okay.
And then it would only get an error after reaching the base case and going and being on its way back up.
Okay.
So you have to imagine, here's our call. It recurs. It does a recursion. It does a recursion. It does a recursion. Base case go up, go up, go up. So only, so yeah, if you're saying if this part contains an error, it would crash exactly here.
Because nothing is instantiated yet, so it wouldn't know if there's an error, right?
It's because none of those calls on this side have actually reached the second part yet. They're all still
Yeah.
busy doing this.
Okay, okay, now I get it. Yeah, it's basically the same thing I asked earlier, but I just wanted to be sure 100%. Thank you.
Yeah, no problem. It's good to ask questions about this just to check if what you're understanding is correct, because it's really complicated. With that said, let's try to do the first task. This one is not that difficult just yet. The task is modify the previous rule to do multiplication instead of addition. So approach, not necessarily for this question, but for recursion in general, is first consider the base case. When should you stop doing recursive calls, and what should happen when it reaches that point? So what should be the state of things by that point? Then the body, what and where should be the recursive call, and what should be the rest of the body? What should the rest of the body do? So let's go back to the sum example, and I'm going to give a hint. There's two things we need to change, not including the obvious name change. What two things should we change to make it do multiplication instead of addition?
The base case and how your final value is calculated.
All right, and how should I change them?
0 goes to 1 in the base case.
And why?
Because you have to get to the end and then times that value back, and timesing it by 0 would just make it 0.
Yeah, exactly. So if you do everything to, if you have a 0 in the base case, it will return 0, and it would just everything would just be multiplied by 0. And what should we do in the body?
Add a multiplication sign instead of the plus.
Yeah, so this should be a multiplication. Correctly, that would change it to a multiplication. Everyone else who hasn't asked questions up until now, is it clear? It is really difficult. So if you're not entirely clear, please just ask.
So if let's say I got a question I already asked earlier, if that's okay.
Yeah, sure.
But so in the base case, instead of like the second value, like instead of a 1, you put a 2. It only adds 2 instead of 1 to the value, right? So if you do multiplication, it does change like the total sum, of course, in the end. So I guess you only do 1 because it doesn't have any implication in the total sum, right? So if it were a 3, then the sum wouldn't be the sum because there's a 3 in the beginning, right? Am I understanding that correctly? That's where you're doing 1 because it has no, it doesn't change anything. 1 times 10 is still 10. Well, 2 times 10, of course, isn't 10.
Right. So it's more, the base case is more about where do we want to start, right? So if you do addition, we want to start at 0 because that's just the starting value. And then we do well, not an equal sign. Then we do plus something, plus something, plus something, plus something. The problem is if you do multiplication, we cannot start at 0 because 0 by 0, anything divided by 0 is 0.
Yeah, of course. Yeah.
So then what we want to do is not change the numbers at all. And the way to do that with multiplication.
No, exactly. Yeah, okay. Yeah. Then okay, I get it. Thank you.
All right. Well, in lack of other questions, I will move on. Yeah. So here's the answer again. I haven't put it in an IDE in like a program, but my guess is that it wouldn't be able to handle empty lists very well, but that's we don't really care about that anyway. So how do you learn recursion? Practice is really essential if you want to actually to be able to actually write them. And I'm going like I noticed that it would be very useful to have a step-by-step guide on how to make it, but I don't have such a guide yet. So like the previous group already suggested, I would have something like that. So I will try to have a more in-depth guide on how to do recursion for the next time. But some tips that I have in the meantime is, of course, start with the base case. What should be the state of the list when you reach the base case, right? You can have multiple base cases. That's one thing. So when you have more complicated Prolog code, it can happen that there are multiple states in which you would consider that the base case. If the recursive call comes first, it means you already assume it returns the answer, right? That refers to the unintuitive way in which how we place the recursive call. What I mean by that is when writing it, the rule is in this order, right? First, we of course make the head. Then we assume something already gives us the result of the recursive call, and then we calculate it. And that's unintuitive. That's basically what I'm trying to say. But sometimes when writing it, what you would do is you would first make the head, then skip over this real quick, write down the calculation, and then figure out how to make the recursive call. So like that's just my a little bit of advice for making recursive loops. Right. So ideally, there would be another not too complicated question. However, I haven't put that in this slide yet. So we will focus on really practicing with it next session. And this session, I will just give all the theory. So you guys can already think about it before we actually start practicing the things. So there are two more, what were they called? No concepts that are important for recursion. It's called tail recursion and accumulators. Tail recursion means that the recursive call is at the end of the rule. And this improves efficiency. And the reason it improves efficiency is if I draw the thing again, where you have a recursive call, you start, you make a recursive call, make a recursive call, make a recursive call. Base case, what happens in what happens is once you reach the base case, you have to go back up because all these rules still have to complete this. So you still have an entire stack containing all these open requests that haven't been closed yet. But having the recursion step at the end, what it would do is it would remove this entire part because every rule ends with calling the other rule, and yeah, every rule ends with calling another rule. Does that make sense? So that's why tail recursion is sometimes is sometimes desired. Not that prolog is efficient to begin with, but it just makes it more efficient. And it also somewhat reduces the chance of infinite loops. But this is not really, this is not a guarantee, of course. Now, can someone tell me why we cannot just go ahead and take this term and put it here? What keeps us from just immediately doing that? It might
I
help
think it
to-
will. I think it will just. No, never mind.
We don't have a value for result
Oh yeah, good one.
And why is that a problem?
because R is H times result. So there'll be nothing in it.
Yeah, and this gives the same error that we saw before, right? Not sufficiently instantiated.
Okay.
So is evaluates the right side. Result is not instantiated. That gives a problem when evaluating. Big E for error. So to make it a total tail recursion, then we will need something else. It's called an accumulator. Accumulator is an extra variable that accumulates values for the answer during recursion. So the way our recursion currently works is we don't receive the answer until we've already reached the base case. But ideally, we want to accumulate our answer while doing recursion. And once we've reached the base case, then we want to be done. But for that, we need an extra variable to actually keep track of our progress. Because if we do not have an accumulator, we are relying on the call stack to save the answers for us. Because I haven't said what a call stack is yet, the call stack is basically all those rules waiting to be finished that are calling each other. So let's give an example. I'm not gonna ask you guys to write it, so because it is a bit of a step too big. So I'm just gonna write it instead. Rewrite the sum to use tail recursion using an accumulator. Do not look at this one yet. We'll look at it at the end, just to make it a bit simpler. We made a new rule. We call it sum A. Sum A contains, we call it using a list, the accumulator, and the result. We'll take a look at the base case at the end, but it's the same principle. We reach the base case once we finish the list. Okay, so what is the idea here? We give it a list, which is separated into the head and tail. We give it an accumulator, and we give it a sum. Now, ideally, or basically the way to properly use this function is to give it a list like 1 and 2 again. We set the accumulator to 0 because we start at 0. And then we give it our empty variable because we want an answer for our sum. What's going to happen is it's going to say new accumulator is accumulator plus the head. New accumulator is empty, but that's okay because it's on the left side of the is. Accumulator is 0, which is instantiated, plus h, which is 1. No problem so far. So our new accumulator is 1. Next, we're going to do the recursive step again. The recursive step, what it does for us is we're going to call the sum again with only the tail. We're going to give it the new accumulator, which is instantiated, so we're actually giving it a number. And we're giving it the sum, which is still empty. Right. And because this recursive call is at the end, after calling this rule is finished. So it can just be removed from the call stack. So it's more efficient that way. All right. Next up, we've called it again, basically. We called it with the accumulator, with the list being 2, the accumulator being 1, and the variable being x. What happens next is not a big surprise. Just erase some stuff. New accumulator, which we don't know yet, is accumulator, which is 1, plus the head, which is 2. New accumulator is 3. We're going to call the sum again with the empty list, because we've already reached the end of the list. New accumulator is 3. The sum is, hey, a new empty list. That means we have arrived at the base case. Right? Well, since we arrived at the base case, what's going to happen? This variable contains a 3. And this variable contains empty. They're the same variable, so what's going to happen is Prolog instantiates the x for 3. Right? Because it instantiates x for 3, all other recursive calls receive 3 as a sum. What we've basically done, we've moved the value of the accumulator to the sum, because that's where we expect to have our value. So the final answer is x equals 3. Any questions so far? I kind of find it hard to believe that the explanation was so clear. Is everyone sure they understand it?
I have maybe one question. I missed that part a bit. Like the sum a open bracket or open squiggly thing L A R. Is that part of the? That's not part of the. What do you say? Of the knowledge base. It's just like an
No, that's just,
example, right? Yeah. Okay.
That's just how you write. That's just a notation for the function,
Yeah.
so people know how to use it.
Okay, great. Yeah, I already thought so, but I just wanted to make sure. Great.
You'll see a real example of that in the exam question. So, all right. Well, since everything is clear, let's. I had a promise to explain what this line is for. It's not actually difficult. I just figured it would be better to not make things too complicated. So, for convenience, since we assume we always want to start at 0, accumulators usually come with an extra rule that initializes the accumulator for you. So we have the original sum rule here. You just put the list and the empty variable for the sum, and all it does is it calls sum accumulator for you. So same list variable, it puts a 0, because we always want to start with 0 in the place of the accumulator, and then the same variable for the sum. But these are just convenience, initializing rules for convenience that are usually included with accumulators. All right. I think we can move on. So this is the exam question. This exam question is the way it's structured. Is they give you a predicate. We'll go through it in a minute. And the predicate is a bit more complicated than what we used to so far. And basically, it contains left recursion, which is the opposite of tail recursion. Forgot to mention that earlier. And then they ask you to make it into tail recursion. And they don't tell you this, but you would be using an accumulator for this because that's the solution you learned for this. I noticed in the previous class that is not really realistic to try and make this today because this is such a big step and this is really like a high level because it's already like exam level. So I would suggest we leave this for next time. Although we could just go through the original function and then we continue on to the theory. What do you guys think? So 3 options, I guess. Either we just try to do it anyway, which I don't recommend, or we just only go through the function as it is and try to understand it, or we just skip the entire thing and move on. All right. Anyone else have a strong opinion? Because otherwise, I'll just move on. All right. So we have reached the end of prologue. I know it felt like forever. These are just some important terms. There is a chance that they'll have a multiple choice question where they will test your knowledge of these terms. So read through them, make sure you understand all of them. And if there's one that you don't understand yet, please let me know. All right, looks like everyone understands these terms then. So we have reached the end of prologue. If you guys want another break, let me know, but I think it's okay to just move on. Our sessions ends at 4. But yeah, if people want a break, just let me know. I'm fine with whatever. It'll also be like a shorter break, like 10 minutes or something.
I'd like a short break. That's okay.
Yeah. All right. Yeah, so let's reconvene at 25 then. And
Can
yeah,
I
so,
ask a question in between?
yeah, so I'll be
Oh,
here for questions during the break as well.
okay, great.
So we just type the break times first. Right. Yeah, so break until 25, and I'm still here for questions. What did you want to know?
Yeah, can you go back at like the tail recursion part? So
Let me check
yeah,
this
here.
part or this part.
One after, so one before. Yeah, this. So you said like the same with like let's say with marble, you need also initializers. You use one time, you see it one time, so you know what's in the. So you have this about. It's basically the same, right? You have the knowledge base for my perception. So the first rule, the sum list sum had, and then the body sum a list zero sum. That's used one time, then the rule is sufficient as a way, and it doesn't go over it anymore. Do I understand it correctly or not? Because
I'm not sure what your question is.
so you said like the first part of here. So if you there are three rules now, two rules and one fact, as you stated. So the sum list sum, and then dot slash sum a list zero sum. That only initializes the recursion part. So the whole thing, right?
No, not quite. It's just all
Okay.
three are just part of the knowledge base.
Okay.
So what would happen is if you call
Yeah.
the sum A, for example,
Mhm.
because you feel like using a different starting point or whatever the case may be, right? Then it will go through the entire knowledge base, including this one.
Oh, wow. I'm not looking correctly. I now see what it is. Wow. Yeah, no, I get it. Because I was looking at, I didn't see that, like in the second rule, at the end, it says sum and not sum A. Oh, it's,
Oh,
yeah, it makes sense now.
that's actually a mistake. This should be sum A.
Oh, there should be. Okay. Oh,
The
okay.
slides are not
Now,
perfect.
okay, now that's fine. But, so it goes over it. So, like, okay, so because you went maybe I missed it. So the first line, the sum list sum, that instantiates the accumulator. When is it used? Because it's the first line, so it goes over it first.
It's used when you specifically query
Yeah.
for the sum instead of sum A.
Okay.
So it's just like in all the way at the beginning, it's just like basic search, right? I
Yeah.
query a rule or a fact, whatever.
Okay.
You
Yeah. Yeah.
query
Yeah.
it,
Yeah.
and it will look for the entire knowledge base and look for a fact that matches the
Yeah.
same name.
Okay. Yeah, but you do need like an initializer for till recursion to work, right? Or it won't work.
No, you could just ask, you could just make a query.
Yeah.
You could just make a recursive rule and then directly ask for it. You can also, this one is not needed, it's only for convenience, right?
Yeah.
So we're only making an initializer because we don't feel like typing 0 every time. If you leave it
Yeah.
out, that's fine, but we have to remember to put the 0 there. I see a question in the chat. When would you do the left recursive rule and when would you use tail recursion? So I think as far as I know, it's not, it's just how you deciding how you design your rule, right? So for example, sum can be done with either, and they both achieve the result, but you would try to make it tail recursive to improve the efficiency. But there might be other more complicated recursive rules where only one of them works, or only left recursion works. So for some, both of them would work, and for multiplication also both of them would work. But this depends per what you're trying to achieve. How can you recognize it? I think we should get into this when discussing in detail how to write recursive rules, because I don't think I have the material right now to explain it properly. It's also for a large part, just practice because just like with designing Python functions, I can explain some conventions and some tips, but you really have to practice to be able to write it properly.
Another question I have actually. So let's say I'm making some recursion exercises, and I'm stuck where I don't know the reason um, why it fails. Can I send an email or something like that, or
I think this is the best for the group chat, for the WhatsApp group
okay,
chat after the class.
yeah? Can I just go just put it in the group chat and
Yeah.
that's okay? Okay, great. Just wanted
So
to
the group chat is really meant for if you guys have any more questions while you're studying. And
Okay.
I can answer, but other students can also answer. You can also just discuss things as if it's a study group, I guess.
Yeah, okay, basically. Okay, thanks. Great to know.
No problem. I'm also gonna get something to drink real quick, so I'll be right back. Oops, I'm 1 minute late. Oh well. I'll just wait just 1 minute till so everyone can prepare mentally for more multi-agent systems. No more Prolog though, because we're done with Prolog. For now, anyway. Does anyone ever really understand Prolog? Right. So we are done with Prolog. I said that like 3 times by now. We're gonna continue with a small amount of theory about agents and environments. So there you can expect 1 or 2 questions about just simple questions testing your knowledge about agents and environments. And if you just remember these couple of slides, I think that's about all you need to know about it. So first, what is an environment? Right, so you have the environment is the digital setting of whatever the agents interact with. It's the world. I think the best way to see this is as a video game because that's about what comes close to it. So the world, the server is the environment, and the agents are the beings that interact in the environment. There are 5 characteristics of an environment, and these should look very familiar from intelligence systems. So you have deterministic, stochastic. So deterministic means that there's no element of randomness, and stochastic means that there is an element of randomness. Specifically in multi-agent systems, it's defined as if you know what the agent is going to do, can you calculate exactly what the environment is going to do as a response? And if the answer is yes, that means there's no randomness. It means it's deterministic. It means you can just determine the response you get from the environment. Discrete or continuous. So is there a finite amount of states or is there an infinite amount of states? Can I think of a video game? Yeah, imagine there are objects and they can be put in infinitely many places, right? Because you can just always move them 1 pixel and then it's an entirely new state, something like that. While, for example, chess has a finite amount of states, so it's discrete. Single or multi-agents. How many agents are there? Well, imagine if you're playing solitaire, it's single agent. Imagine if you're playing chess, it's multi-agent. I think this speaks for itself. Static or dynamic, does the environment change without agent input? Well, with chess, it does not. But if you're playing a recent video game, then it surely does change without agent input. Fully or partially observable is all information available. Also speaks for itself. Fully observable is like chess. Partially observable is like a modern video game because you can't see everything at the same time. Questions about this? This is, I think, really simple stuff. Right? Anyway. So the agents interact with the environment using actions, and the environment interacts with the agents by giving it percepts. So percepts are just bits of information that the agent receives from the environment. They're kind of like events, I guess. You don't need to know a lot about them. There isn't too much to them. Just know that there's 2 types, send on change and send always. Send on change means that the notification is only sent when the situation changes. So imagine if there is a package delivery or something, and there is a package and there is a the state can be either there is a package or there isn't a package, and it only sends a percept if the package arrives or something.
Aren't there 3?
Did I miss one?
Yeah, because you have like the initializer, you have to replace, so you have to add, you have to initialize with it, you have to update with it, and if it's always, so with the update it's only on change, and replace is always, and add is only used once, usually for initializing things.
But that's not a percent, is it?
Yeah, it's something it's like information from the environment you send to the agent, right? Put it in the knowledge base.
I thought
get
the
it
agent
correctly?
always puts it in the knowledge base, but it doesn't receive it from the environment.
So yeah, I don't know. I read it in like the marble thing, but I have to double check just to be sure. But I thought
I
there were
mean,
like 3.
I'm not saying you're wrong because
Yeah.
I had Go last year, so maybe
Yeah.
something's changed.
So if you like in the MOS file, right? You have to put the percept, so what it sees. So you can, if you run, let's say, whatever, they usually use blocks world or something like that as an example, and you want to see what's happening like in the environment, like in the, also you do like either you add it, you replace it, or you update it, and that's usually based on how it sends. I'm bad at explaining things. I'm sorry, but
Yeah, no,
that's
it's okay.
how, like, while
think-
making the exam, the assignment, this was like a thing.
I think I should check up on it, and I'll let you guys know when. Yeah, I'll look it up. But I was also not talking about Marble yet. This is more like the theory. And as
Oh,
far
I'm
as I
sorry.
know, there's only 2 kinds of percepts in the theory. But I'll check. So yeah, send on change and then send always. These are percepts that are always sent. So how often the system updates percepts equals how often the agent receives them. For example, there's a temperature gauge, and there's agents always updated on what the temperature is or something like that. And if I'm correct as well, whether it's on change and whether it's sent always is a design choice. So it's not necessarily that you can read the type of percept and then immediately know if it's sent on change or sent always. At least what I can see from the practice exams, they usually tell you if it's on change or sent on or set always. Then there's actions. They're actions from agents is how they interact with your environment, and it can be either instant or durative. Instant actions are, well, performed immediately with no time in between, and the effects are therefore also immediately perceptible. It can also not be interrupted because there's no time in between to interrupt it. Then you have durative actions. The action takes time, which means that the effects can only be perceived once it's complete. And because it's not instant, you all, of course, have time to interrupt the agent while it's trying to do it. So instant actions are easy because they cannot be interrupted, but durative actions are complicated because they can be interrupted. And there's 3 things, as far as I can tell anyway, that can happen when you interrupt a derivative action by sending another request to the agent. So yeah, I'm going to use the block words example as well. It's a simple example. But imagine it's trying to move a block. While you're moving the block, another request to move something else is received. Depending on how you design the bots, of course, this is a design decision. The request can be ignored, so the bot will say, "I'm busy, ask again later." It can be overwritten, so the bot puts down the current block and immediately goes to the next block. Or it can do them both at the same time. And this is not really possible in block worlds, but imagine a more recent video game, an agent can be walking and at the same time shoot. So imagine if the agent is already walking, so it's what's it called? Processing a walking request. And whilst walking, it receives a request to shoot. Well, it has legs and arms that are working separately, so it can shoot while walking, and it will not interfere with each other. Derivative actions can, of course, fail halfway through, while with instant actions, you can immediately tell if something failed. With derivative actions, you need to actually monitor them, just in case something goes wrong, because it can happen at any time. But as far as I can tell, you will not actually have to program them being able to deal with it. You just have to know that this is a thing. Right, that was it for the theory. I didn't miss any bits of theory, did I? That don't have to do with Marvel. Don't think I did, but let me know if I did, and I'll come back to it next session. If you guys even want to talk about the theory, because I can imagine that you guys say I'm just going to read the slides or something, and we'll do recursion or something in this session. Can you please show the last two slides, please? This one about actions, you mean? And I'll show the next one in a second. You also receive the slides after the session. And this one, I don't know how. Right. So this was what I had planned for today, but I could also give a short introduction for Marble, or we can do more questions or whatever you guys want. Any ideas? If there are no ideas, I'll just make a little start to Marble. Just do a quick overview. More questions related to the exams. Which part though? When we will do the exact question that you skip, we will do it next session. So once we know a little bit more about recursion and more practice with recursion. Marble. All right. Getting slightly conflicted messages here. I'm checking if there's any useful. I'm okay with what the majority wants. Yeah. All right, I'll just do a quick overview on Marble and see how much time we have left. So about Marble, because what Marble is it's like a framework built on top of Prolog to give it extra functionality, like working in real time, agents being able to perform actions on the environment, basically extra functionality based on top of Prolog. Last year we had Goal. Marble is the simplified version of Goal. Goal was not popular, largely because it tried to take Prolog and use it as if it was Python, which just made everything more difficult. It was also badly made and just really complicated. So I hope Marble is somewhat better. We'll talk about the files we have in Marble first. It has like half the files Go had, so that's one improvement they already made. So you have 4 files in Marble. First, you have the Prolog file. This defines all the rules and knowledge, just like it does in normal Prolog. You have the object.mass2g file. So with object, I just mean whatever bot you're trying to make, right? So in the practice exam, they use a security bot or something. So security bot.mass2g. In here, you set up the environment, so you import the environment, all of that stuff. That's not really important for the exam. The only important thing for the exam is that you use the mass2g file to set up the channels by which to receive presets. Then you have the object init. This is like the init function for a class in Python. It makes the initial state of the agent. So usually there are certain variables that you want to have accessible at the start already. This is almost always the case. Stuff like a starting position or a starting state. Then you have the object.mod2g file. This is the main file, you could say. This file contains all the decision making and all the possible actions it can take. And I believe, but I still have to check this, that it gets called every time a new preset is received. But since Marble works different from Go, I had to double check that. Let's look at the product file first. So there's 3 aspects to it. On top, you will usually find the dynamic definition. So the dynamic thing just defines a bunch of predicates that can be added and removed from the knowledge base on the run, so while the agent is running. So for example, position, state, and alive are 3 things that change and that can therefore be added or removed from the knowledge base. You have normal facts. In Marble uses these as constants, so these don't change while running. And then you have the rules, which also don't change, and you can see them as utility functions. For example, the sum rule that we did recursively, it, for example, also does it does something. It gives us functionality, and the rules here do the same. So how do I say it? I can imagine if people were like, what are rules even used for? Well, they're like utility functions in Marble, for example. Then we have the mass2g file. Like I said, I still have to do some reading on what changed between Go and Marble, but the mass2g file initializes everything, creates the agent and all that kind of stuff. That part is not important. The most important part is making the channels for the precepts. So send on change precepts are made using the keyword update. So imagine it's a predicate called I don't know, delivery. It's only sent on change. You would write something like updates delivery /2 because it takes 2 arguments. And then there's a set always precept. Yeah, that there you use the keyword replace. And imagine if we are alive or dead can change anytime, and it doesn't have any predicates, so we would write something like this. I mean, it doesn't have any input arguments. I'm not going to go too far into how to actually write the rules. But one thing to remember to think about already for next time is the structure of the mod2g files. What they contain anyway is rules for rules that actually do something, and I'm just going to call them actions. And the way they are structured in Marble is you have an if then or for all do. So every action should have a condition, even if the condition is I should run always, you still need to put the if, and you just put if true. And the way it's structured, if you have an if, then you would have the condition. The condition is also the place where you instantiate your variables if you need information from the knowledge base, and then is where you actually change the knowledge base or perform some action on the environment. If, for example, you have a bunch of different presets that you want to all do, for example, for every position, you do something. Then you would do a for all do. So for every thing where the condition applies, do it multiple times. Like do it for everything that is true, while the if only does it for one. I believe there's an example here. Yes, there is. So this is an example from Marble. If states and not alive. So this would be the condition. Then insert, which puts a new bit of knowledge in your knowledge base, and then delete to delete some other part of the knowledge base. The syntax is also different. Is it not bad Marble writing since you always need to delete first? It might be. That might be the case. I did not think a lot about the example. It was mostly about the syntax. No, but it's a good point to make. I should probably change it for next time. Because you would probably end up deleting what you just wrote, right? That's what you probably write. You would do that. Basically, yeah. I might have made a mistake there. Okay, so I also just wanted to show an example from Go last year. It's like this is from the project multi-agent systems, and it's a whole mess. Yeah. Wait, I got a message, another message in chat, but did we talk about when add is used? Where did you get add from?
The slide before this, you were talking about replace and update, but there is also add, right?
Yeah. But I'm not sure.
That's only,
Yeah.
yeah, so that's only when it's like used once. So in some cases, like if the environment is deterministic, static, and like fully observable, so it won't happen any weird things. You only need to see the environment once to know if to know what happens. So I think the case with you put the blocks on each other. If you once see how the environment looks, you don't need to get updates anymore because it doesn't matter. Because if you write what you write is true, then you don't need to get updates and those kind of things. So then you can use like initialize it once, like the environment, by using add, and you get it like one time in your knowledge base, and it will stay there because it won't get removed and it won't get updated. So that's more than enough to know your goal, to know your initial state. Yeah. I think
Right.
what I'm saying now is correct. I can be wrong, so double check the Marble guide.
Okay, thank you.
Yeah. I'll be a bit honest. I received the file with the Marble specification way too late. so I haven't had the time to get everything from it. Because like I said, it's new this year.
I
But-
get it. I get it.
Yeah, that's why we're gonna do it on Wednesday, because then I will also have like a deep dive on how the specifics work. But this was more just an introduction. So we have 10 minutes left. Appreciate time. Yeah. I mean, I've already learned goals, so it can't get much worse than that. I mean, if you look at what I had to go through last year, it's not nice. Anyway, since we have some time left and I didn't have any other things on the planning, I think it's a good idea to do one more exercise, but I'll have to quickly look up. Is there any topic that people would like to practice?
Doing prologue never hurts. Exercises.
For prologue, left tail recursion. Yeah, okay. Left tail recursion is a bit of a. All right. I'll have to quickly look up something because I didn't have enough material for this one. Let's try to do it all together. Let's try to make, I'll open a notepad real quick, make it just a bit bigger. Let's try to make a recursive rule that calculates the mean of a list of numbers. I'm just making this up, so I don't actually have the answer right now, but maybe that's also useful to just quickly try to do it together, right? So at one point, let's start with the base case. Imagine if we have a list of numbers and we want to calculate the mean. What should be the base case? Any ideas? When should we stop doing recursion?
At an empty list.
Yes. So let's just call it rec or something. The base case will be if the list is empty, then something, right? We'll get to that later. So the input should be like a list and at least a mean. So the way we want to use it, I'll add a percentage sign so it's clear that it's not code. A list, and we should get the mean back. We should also probably have a term for the length, because you can't calculate the mean without the length, right? And yeah, so
we use an accumulator.
yeah, let's try to let's try to write it first, see what happens without the accumulator, and then we can change it into the accumulator. I think that's slightly easier. So what it does is it receives a list, we put it into a head and a tail. The head and a tail, and we have a length which we don't know. We're not going to actually give it the length, that would be too easy. And we also don't know the mean. And then we would probably immediately begin with the recursive step. Right?
Depends how you want to do it.
Hmm. It's been a while.
So
Any suggestions? I would also.
I think
really-
we do it with the recursive step first, no?
Yeah, so it's kind of like summation, except
Yeah, like some.
yeah. So
but, oh, yeah. So you want to count with one. You want to each recursion. You want to do a +1 with one, right? And with the other one, you add everything together, and at the end, you have to divide the one by the other. That's how you basically get it, right?
yeah, the problem is
The dividing part. I know.
yeah.
So that's why I think you make like an accumulator, like an extra rule on top, and that's how you try to solve it,
Hmm.
I guess. Yeah, I think so. So after this, so now you write this rule and then you reference to a new, how do you say, rec2 or something on top. And there do you do like all the counting and everything. And then at the end of this rule, this is how I think you have to do it. You divide the number of times it had to add by the sum of the list, and then you have it.
Yeah, I get what you mean. So you're saying that
Yeah,
you would make a second rule that would sum how many elements there are and the sum of the elements.
exactly.
And then yeah. So that would probably be that would work. But you know, I'm kind of thinking
You can also use length and cheat, but that's not nice.
yeah, of course. Prolog also has length. Well, our version has anyway. But I'm thinking like I should also like it's been a while that I actually did recursion like in Prolog. And I'm not sure how useful what we're doing here right now is. And it's already time anyway. But yeah, shall we just say that I'll actually have some practice material ready for Thursday or for Wednesday, so that I can be a bit more useful than this. And I also have the answer for this one, but I'm not gonna make it to write it really fast now. All right.
We need 4 elements for this as well, because you need the sum.
Yeah, exactly.
And this would probably take a while to write. Will probably be good homework. All right.
Cool.
We'll leave this forward to this then.
Thank you for today.
Yeah, great. Thanks.
I had a way deeper understanding of Prolog from your tree thing.
Yeah, thanks. That's good to hear.
Same.
Yeah, so thanks everyone for today. I do have to say this explanation went better than the first one, but that's always the case. If you guys have any questions, feel free to use the WhatsApp group chat. I think everyone's in it by now. If you have any feedback, because this is of course the first time Athena Studies has done multi-J systems. Any feedback is welcome. Any suggestions or requests for next time are also welcome. And if there are no further questions, I'll see you guys on Wednesday.
Thank you. See you Wednesday.
See you
Bye, guys.
Wednesday.